This conference will now be recorded.
So just to summarize, basically we have application, then we convert it into assembly level language, and then to machine level language, and that machine level language is going to run on x86 architecture or ARM architecture or Risc-V architecture, right? So these are various hardware architecture, the processor architecture. It can be like ideally, like when I say different architecture is x86, ARM or Risc-V. Ideally, how the instruction sets are implemented, or how the pipelining is implemented, how the vector processing is done. So these are the scenarios how actually these architectures are differentiated. Based on these scenarios, these architectures are differentiated. So whenever we talk about any of the processor design, right, there are two aspects involved in it. One is software design, another is hardware design. So in software design, or also we call it as like in case of processor designs, we also call like embedded design also, right? So in that scenario, we mostly talk about like how to deal with interrupts, how to write a software code for pipelining, how to write a software code for threading, how to write a simple code for certain operations. So we deal with like various software scenarios, right? Uh, I mean, when I actually think in terms of software, I mostly think about like how the resources are present, what resources are present. I don't think much about like how these resources are optimized, right? But whereas like when I talk about hardware, I mostly deal with like how this architecture has to be designed, how this pipelining has to be designed such a way that like when I run my software, it will be running faster, right? So I also need to think about what kind of vector processing architecture has to be implemented, or what kind of accelerator I have to implement, right? So how much power it is going to consume, what is the maximum speed with which what I can operate if I implement particular architecture, right? Uh, or like how I have to verify the whole environment, right? So ideally in this course, like what we will be doing, we start with understanding the software, right? Because like let's say like when I want to implement a hardware, based on like the way how various instruction sets has to be, based on that we implement the hardware, right? So we actually the Risc-V is defined like Risc-V standard. We'll also see that like whole history, how they have designed, and like what are the various standards they have put. So they have defined various standards. We call it as instruction set architecture, ISA. So they have defined like how the software should be, what should be the instruction sets, and what are the different operations should be proposed by Risc-V. So based on that instruction sets, what they have defined, later point of time we have to implement this hardware in RTL, right? So initially we look into like various standards, what is defined by Risc-V. Then that standard, we see that like how to implement ALU for that standard, how to implement decoder for that standard, how to implement cache architecture for that hardware, right? So that we will be looking into, and like how we can build a verification environment for this Risc-V architecture what we have developed, right? So when I say like instruction set architecture, uh, like usually a C program what it is written across the x86 or like ARM or Risc-V, that may not be different. Like I mean the C program is same across all the architecture, but how it is mapped to instruction sets, that is assembly code, and that assembly code how it is converted into machine level language, that who takes care usually? Can someone tell me who takes care of that? Like converting this high level language into uh, assembly, and from assembly to machine level language, who takes care usually in
Interpreter
your software?
assembler, right?
Yeah, assembler. Generally, like compiler, what we design, right? So
Compiler.
x86 has like x86 has its own compiler, whereas Risc-V has standard tool chain which is developed by Risc-V association. So they have their own compiler. So this compiler takes care of it. But let's say like you design one architecture which is of like having like which is having a new extension, that is something like you are, let's say like you are working on some high speed FFT accelerator, so it requires some extra interface, right? So then you have to develop certain software. I mean, like on top of this compiler, you have to define certain extensions, which whatever the software code you write, so that should map into that. So usually we go for like some kind of memory mapping or AXI mapping, right? AXI memory mapped interface or like streaming interface. We go with various extensions there, right? So all these aspects we have to look into. But initially, the starting point, what I can say, we have to start with understanding this instruction set architecture. When I say that, like I'm understanding this instruction set architecture, again, I have to start with some kind of software coding, and I have to use existing tool chain. That is like one is Risc-V tool chain Excel, which is given by Risc-V, and they also have an official debugger called Spike, where you can see that like in a standard Risc-V processor, whatever the software code you have written, when you program into that, how it behaves, right? So that Risc-V simulator they have, that is called Spike. So in Spike, we will be looking into like what are the various scenarios, how it is behaving, all these aspects we will be looking into. Once that is done, so ideally what we have to do, let's say like you have designed one RTL code for that, okay? Risc-V processor code you have written. So your Risc-V processor should behave the way how the simulator is behaving. So those who are in verification, you might know how usually we verify. So we'll have one golden model, and we also have some kind of designed hardware. What we do, we generate certain test vector from the golden model, and we feed that into our design and test, and we get some output, and again we have to compare that output with the golden model, right? So that is how we actually verify it. So let's start getting into detail how this Risc-V is different from other architecture, and like why we are going to use this Risc-V, right? So certain aspect we will be looking into. Then I will also, in today's session, I'll go through what are the various aspects we will be looking into in our entire course, and what is the approach we will be following. Okay, so that we will look into. So Risc-V is basically a open standard instruction set architecture. When I say open standard, like if I consider ARM architecture, if ARM architecture is if I take IP from ARM, so it has to be properly licensed, right? So like let's say even if it is a simple microcontroller architecture, I have to get a license from ARM, and I have to pay royalty for every IC what I produced out of this ARM. But now when I say Risc-V, it is an open standard. You can take this repository of Risc-V or like instruction set architecture defined by Risc-V, and you can build your own Risc-V processor, right? So here you need not actually pay any royalty when you actually produce multiple ICs. So can you name or like can you give me some examples which you might have heard about Risc-V processor? Already it is in manufacturing stage, right? I mean already it is commercialized. So Risc-V processors are in market now. Can you give me some examples what you might have heard? Anybody heard any of the Risc-V processor which is in the market?
Shakti processor is, I think, based on this only, right?
Yes, Shakti is one of the processor from IIT Madras.
Vega
I mean, out. Pardon, Nikhil.
and Vega processor proceeding.
Vega processor, yes, they have commercialized Vega processor. Even evaluation board of low cost is available. If you go to Vega website, so you have like various evaluation board where you can actually get these evaluation board like Arduino kit where you can program this Risc-V based software into that. Also, you might have heard about Sci-Fi company, right? So where they have built their own commercial processors as well. Now, even like companies like Qualcomm, NXP, they are also getting into this Risc-V scenarios. right? So ideally, initially it was like maybe like before 2020, I can say it was majorly for research and educational purpose. Now, when uh, the things actually becoming more stable, RISC-V architecture is becoming more stable. Now, RISC-V is getting standardized, and like many commercial companies are also using this RISC-V architecture. Now, if you see that, like companies like Netra Semi, startups like Mind Group in IIT Madras. So these are like some of the startups who are actually got huge funding, who are actually building various vision processor out of this RISC-V. They are also building some real-time application. Like one of the company I was like recently hearing, they are building some kind of radar-based processing system using RISC-V architecture. Now here I need not pay any royalty to ARM like for every duplication or like every IC what I produce, right? So that is like something like I have my own flexibility to build or modify the architecture. So that is one of the major advantage of this RISC-V. So it enables full customization. You can completely customize in your own way, where you can implement accelerators and your own custom instruction sets, and you can build your own processor. So that helps lot of innovation. I mean, if you see like lot of government initiative, like if you see 20th by 20th there is one hackathon is going from government of India, RISC-V hackathon. So they are actually supporting some 100 teams, and they are funding around like 1 lakh for each team for building various application on top of RISC-V. These kind of innovations are happening, especially since it is like open source. We have a lot of room to implement a different application on top of this RISC-V, right? So initially it started as a college project, like in RISC-1 in 1980s. So if you see that like the timeline, so it took long time, but like in 2020 they started, 2010 they started RISC-V by UC Berkeley, and in 2020 they basically made like RISC Foundation. I mean, the foundation made like RISC-V International, where the commercialization point started at that scenario. So the key features, it is open source, and RISC-V is a modular architecture. Let's say like in ARM, if I take, so that is the IP which is completely you will be getting, and you don't have option to modularize it, right? So that is like entire architecture you have to use as a IP. So you might get like synthesized model. You are not having access to the RTL code of that, and like you'll not be able to modify any of the architecture. So when I say it is not modular, like if you are from design background, right? So can you tell me like what are the disadvantages? Like let's say like if I take one ARM core, and if it is not supporting modularity, and whatever the IP they give, I implement from the RTL. So what is the main disadvantage I may face there if it is not modular? And whichever is not used certain parts of the instruction set, and still I'm synthesizing that, like what could be the possible issues I may face there?
Basically means optimization for the area, and also that will be difficult, and enhancing the exact.
Maybe like area and my power will be
Yeah, yeah, yeah.
an issue, right? So but here let's say I need a simple microcontroller kind of architecture. If you have seen like Shakti processors, M series is ideally designed for low power application. It is for microcontroller kind of application. So that is very low power application what they have designed. But if you see like they have like high class applications also, I think CEF various series they have built, that is like vector processor. So depending on the application, right, I can modularize, and like I can actually like implement whatever the features I want, whatever the extensions I want. Right? If you see here, like we have starts with the minimum base instruction set. That is what like RV32, RISC-V 32I integer instruction set. That is where like all the architectures which will be having this RISC-V 32I instructions. So that is where like most of the it is something like base instruction which all the processors will have. But again, we have something called compressed instruction set, which is of 16-bit, right? And we also have higher end extensions, F floating point. We also have a custom instruction set, various different high-end like crypto instruction sets, crypto extensions are there. So depending on the application and depending on the way we want to implement, right? So we can highly uh, customize the architecture. So that is where like it helps us in modularity, right? So and ideally, right? So these are all like if you consider x86, if you consider like ARM architecture, uh, the instruction set length may vary. Different instruction set may have different types of length. So when I say the instruction set length varies, so for software it doesn't matter. I mean, like it keeps whatever the instruction it is, so it is going to compile. But that load basically that instruction set variable length, that load is going to fall on the decoder side. So when and that decoder side it is going to fall, so my architecture, hardware architecture also becomes complex. Okay, so ideally this variable in the instruction set it actually hampers my hardware implementation. So that is where this this Risc-V architecture, it simplifies. All the instructions are 32-bit format. In case of 32-bit base instruction, if I'm going for 64, that extends to 64-bit, right? So it basically simplifies my implementation, simplifies my design, since it is 32-bit architecture. So ideally, if I compare the ARM versus Risc-V, so ARM, as you know, like it's open and royalty free. This is like very high level comparison. There are like various architectural level differences as well. So like ideally, like custom extensions, it is fully allowed and encouraged. Whereas like in ARM, that is not available for public course. Okay. When I say public course, which is available for let's say like if they have given an open source code, but you cannot actually modify that architecture and like say that is the ARM architecture, right? So that it basically it's a tied to vendor lock. I mean, in the sense like it is licensed. So ISA is basically highly modular, whereas Risc-V is less modular because like you have to take their IP and utilize as is. Like you do not have flexibility or like RTL access to modify that architecture. And flexibility in case of Risc-V, it is highly flexible. So here ARM, it is a fixed instruction set. Whatever like for a given architecture, they have like various. In ARM also we have C and various formats, right? So they have various versions. So for a given version, the architecture and instruction sets are fixed. You cannot have add or subtract any of the instruction set when you implement it, right? So ideally, Risc-V ecosystem is basically having a software tool that is like GCC, LLVM, Spike. These are software tools what we use for the compilation. So in our course, we basically talk about GCC and Spike. This is for the simulation part, and a simulator like we also use this Spike and QEMU. And when we go for hardware implementation point of discussion, we basically look into like, I mean, we can use model sim for simulation purpose, and we can use Vivado for implementing our architecture on the FPGA platform. So what we will be doing ideally is, so there is a open source IP core. I mean, like one is like, we use three cores. Ideally, we discuss like 32-bit, 64-bit architecture. Initially, we start with something called embedded. So there is an open source core which is available in Git that is called Ultra Embedded. This is a Risc-V architecture which is available open source. So they have implemented RTL verification environment and even like instruction set architecture simulator. So we will be starting with like looking into the architecture of this ultra embedded core. We will be implementing this RTL in FPGA using Vivado. I'll also show you like how we can actually map this into FPGA core, how we can verify on top of FPGA core, what architecture. So with this Risc-V core, right, we will be developing one small accelerator. So ideally, what I do is like I do one small matrix multiplication architecture, which I put it into this Risc-V core, and I show you that like how we can actually design various extensions, custom extensions on top of this Risc-V core. So that we will be discussing. So that is one of the core what we will be looking. And another core is like Shakti base core, that is Risc-V M core. So that also we will put it on the FPGA, that we can put it on the RT board. They have a flow, board flow. So I'll show you that like how we can test it on that hardware, how various application we can develop on top of that hardware with the existing core. And we also see like we will try to modify that Shakti core with our own custom extensions. I'll show you that like how different custom extensions we can develop. And each instructions what we are discussing in this course, we also see that like how they have implemented in the hardware and what advantages we have in terms of like that implementation methodology, right? So that kind of discussion we will be doing in this. So that is one part. And here, coming to the course structure, how it goes. So we in the first day we start with instruction set. As I was mentioning, like we have base 32i instruction set, right? So we start with that instruction set. We also see that like how that is implemented on the hardware, and we simulate the base platform like Shakti or Ultra Embedded, what I have shown. So those instructions we simulate in the hardware, and we also compile on the spike and see that like whether both the performance are matching. So that will go for 3 hours, and we majorly discuss in detail on all these aspects. And one important part in any of the processor design is profiling, right? So you have ultra embedded. I have shown you that like a Shakti processor. So like what basically differentiate the processor, right? I mean like basically like how it is performing, how many instructions per cycle it is executing, right? We usually say mixed profiling, right? So we have to have like various methodology. I'll show you that like in terms of software, how we can actually profile your code, and in terms of like hardware, how we can profile, how we can define like maximum F max, what is the maximum frequency at that like whole architecture is behaving. So all these aspects we will be looking into, okay? And each thing, whatever we profile in the hardware, again we come back to the standard simulators and we compare that, like whether it is behaving as expected or whether it is actually like lesser than like what is the benchmark designs we have, right? So all these things we will see. And we have something called atomic instructions. So that is like little advanced concept. So that things we start like from. So whatever the day I have mentioned, so this is like maybe you can consider it is like sessions wise. So this you cannot, you need not take this part. This is basically designed for like workshops like this. Whatever the timeline I have put, but like usually this will be weekend sessions where every week, right? We will have 6 hours of sessions. So this will be split in that manner. So then we go for privileged architecture. This privileged architecture, especially for your operating systems. So let's say like you are building, like now some of the companies are trying to build laptop processors using Risc-V. In India, also some of the startups are trying this. So whenever I say that like I'm running operating system on top of any processor, I need to have a clear boundary between like what user can access, what operating system can operate, right? So that is where like these privileged modes like MSU, right? So that are like three modes which is available in privileged mode. So how we can actually implement in hardware, how it is implemented on the software side. So those things we will be discussing. That is actually system atomic and privileged architecture I will point. And as you know that like any processor we need software chain to like uh, not before that software chain we need various memory management unit and various interrupt architecture. So we will be looking into like various interrupt architecture, how we can deal with the standard interrupts using software, and also how we can deal with how we can implement that interrupt architecture. So that is also very important, right? So we will be looking into that aspect. So how you can design your own DMA architecture, how you can design your own interrupt service routine. I mean, like whenever ISR called, so what hardware in hardware, what circuitry should be implemented to handle that ISR. So all these aspects we'll be discussing. So then finally, like we'll be discussing with various debug chains, right? So we'll be also discussing with what are the different tool chain we use for debugging aspect. Okay, so I mean, especially this Shakti processor, they use something like OpenOCD kind of platform. So we'll be discussing all these aspects. Like one, like let's say, like my RISC-V processor, I'm emulating on the hardware FPGA. So how I can debug? Let's say like standard processor, like Spike is giving you the standard performance. Now, how I can compare that Spike performance with real-time RISC-V core, which is working on FPGA. So that kind of discussion we will be discussing. And final few sessions, right? We will be in detail. We'll be discussing on debug chains and comparison with the ARM. If you already gone through ARM or x86, in that how we used to do, and like for RISC-V how we will be doing. So that aspect we'll be discussing in detail. Okay. So this everything, the RTL part, which is implemented on the hardware and software, that goes hands in hand. So in the sense, like we will be parallelly implementing on the RTL, we'll be verifying, we'll be testing this instruction set architecture, and in the Spike we will be simulating and comparing the results. So that way we will be discussing. And coming to this part, so generally to start with, in the next session, you have to build your environment first. So by next session, what you have to do is like you have to install this Risc-V toolchain compiler. Okay, so it takes some time. I mean, it takes maybe like at least 1 or 2 hours, depending on your PC RAM speed. So ideally, you can. So the ideal environment for Risc-V toolchain is Linux. But let's say like you have a Windows PC. What you can do is you can use something called WSL, Windows Subsystem for Linux. So let me just demonstrate how usually we do. You have to open the PowerShell. Windows PowerShell. If you are using Windows PC, you have to open the Windows PowerShell. So in that, you have to type WSL. So if it is already installed, it will show all the versions of WSL, what it is installed, all this aspect. So let me just show you WSL version. So it will say that like I have installed 2.2.42. So if it is not present in your PC, right, it will ask for the installation. So you can just install that WSL. And after that WSL is installed, so in the Windows Store, right, you have to install the Ubuntu LTS. So if you go to the Windows Store, so here, if you search for Ubuntu, so here you have to search for Ubuntu, and in that Ubuntu, if you see that 2022 .04.5 LTS, right? So this one you have to install. So here with this, right, you can run your own Linux on top of Windows without like, I mean, usually like people will go for booting mechanism, right? So I mean they split the drive into two, and like one part they install Linux and another part like they go for Windows. Every time you have to boot to switch the Windows to Linux and also. But if you use WSL directly, you can run Ubuntu. So if I type WSL-D Ubuntu 22.4, so this Ubuntu will be launched. So then in that, on top of that Ubuntu, right? So you have to install these command. I mean sudo apt install gcc risc-v64 unknown elf. So this will install a RISC-V compiler. Okay. When I say RISC-V64 unknown, In the sense now what I am building, that is for bare metal OS. In the sense like I'm not building for any Linux or like any of the platform. It is for bare metal. It is like not for any operating system. Okay, so you have to install this particular tool chain, and we will be experimenting various experiments like maybe initially the instruction set architecture, right? So in the next class we will be discussing on like how we can initially like how this instruction set will be implemented and whatever the tool flow I mentioned, right? So with respect to RTL, how we can simulate that. All this aspect we will be discussing and like how to implement like so initially like see the when I say Risc-V architecture, this is standard architecture. So initially we will be seeing existing implemented architecture, maybe 50% of the session. So next 50% of the session, we'll be focusing on how we can modify that instruction set and we can build our own architecture. So that we will be focusing. Okay. So any questions here or any doubt on that flow what I have mentioned? So let me keep session open for next 10 minutes for having a question and answer. Like how if you have any questions regarding this tool flow. Or if you also have any queries, like if you I mean I have shown you that like what is the general flow what I'll be following, right? So but let's say like now you want to have like you want to learn anything additional to this, or like if you are expecting anything more on top of this, right? So we can actually curate certain part. uh, we can like we are flexible for that also. Certain people will have like let's say like some people may have like requirement like you want more extensive discussion on verification, or like if you want some extensive discussion on design aspects, so we can actually add those things also. And one more thing, so this whole uh, um, discussions, right? So it will be project based. I mean, in the sense like parallelly we will be giving you certain assignments. So you have to create your own Git repo, and you have to upload all the architectures, everything in that Git repo, and we will be evaluating that, like whatever you are discussing, right? So I mean, whatever you have implemented that assignment, so you have to put it into the Git repo, and then we'll be evaluating in detail, and we can individually we can discuss and like we can have a discussion that like how you can improve that project and all these aspects. Okay. So any questions here, Sumit, Rambab, Niti?
No, I think
No.
So, is this the same course you are expecting, or like what anything extra you are looking for, like to learn in this course?
Yeah.
no, I think this yeah should be I think good enough only because yeah, I'm mostly exploring in this one. So yeah, whatever it will be
Mhm.
new only.
Okay, okay. What about Rambabu?
Yeah, actually, I was, yeah, it is more familiar to me. Already, I was verifying the same thing with the hardware level modularity
Mhm. Okay,
with,
okay.
with the spike simulator. And,
You are using already using this spike
yeah,
simulator and
yeah, yeah, yeah.
architectures. Okay,
Yeah.
great,
And
great.
also that modularity level with the different cores, M core, G core, and core M split,
Great.
non-pipelining and
Mhm.
pipelining as well.
Okay, okay, great, great. Okay, okay, sure. So just to summarize what we had seen, so ideally like we will be dealing with like two aspects. One is like software part, where we will be like initially we will be going through the ISA architectures and various instruction set architectures, and parallelly we will be implementing this architecture on top of uh, two platform what I mentioned, right? So one is basically ultra embedded uh, system, like where we will be discussing how this architecture is implemented and like uh, uh, how we are actually uh, verifying, how we are actually if you want to add any extensions or how if you want to add any of the uh, accelerator, how we will be dealing, and then finally we will be synthesizing the whole architecture and putting on the FPGA, and we will be emulating and testing. Okay, so that is the whole idea. Okay. Thank you. Then we will. If you are continuing this course, so like from next session, that is maybe like commencing from tomorrow, I guess you can just discuss with the team. So we will start discussing that. Okay. Thank you. Thank you all. Any questions?
No, yeah, thank you.
Thank you. Thanks.
Yeah. Thank you.